In a DC circuit, calculating power is simple. We have a constant voltage, a constant current, and therefore a constant power over time. But in AC circuits, things get weird. With a sinusoidal voltage, we get a sinusoidal current which leads to a changing power over time. And sometimes, if our current becomes out of phase, the power can even become negative. In fact, when we connect a pure capacitor or inductor to an AC source, we see exactly this. Current flows, the generator does work, but the average power is exactly zero. Every joule we put in gets sent straight back by the circuit. So what's actually going on here? What would cause energy to go back and forth like this? Furthermore, if this energy is being sent back to us, how do we distinguish between it and the power that's actually being used? Well, this is exactly why AC circuit theory introduces three different types of power: real power, reactive power, and apparent power. If you studied these before, you've probably seen equations like these, or the famous power triangle. But for many students, these formulas feel like something you just memorize, rather than something that actually makes sense. So in this video, we're going to rebuild the idea of power in AC circuits from the ground up, using both physical intuition and mathematics. Firstly, we'll briefly recap what electrical power is, then derive the idea of instantaneous power for AC circuits. Then, we'll look at what happens in circuits containing resistors, capacitors, and inductors, and see why the concept of average power naturally emerges. From there, we'll generalize the result for any AC circuits, which will reveal the origin of the power factor, and show why it depends on the phase difference between voltage and current. Finally, we'll introduce real, reactive, and apparent power, and see how they combine to form the power triangle. By the end, you won't just know the formulas, but understand what they physically represent, and why they appear naturally in AC circuits. So let's begin with a very quick recap of some fundamentals. Power, in any context, is the rate of change of energy, U, with time. Electrical energy has two forms. When it is static, it exists as electromagnetic fields, and to move electrical energy, we just move charge around. For example, in this DC capacitor circuit, energy is stored in the capacitor as an electric field. This field could only be created by charges moving through the circuit to the plates. To move charges, there has to be a voltage, which the battery provides. The change in electrical energy during all this is simply the charge times the voltage it was moved through. We can say that the change in energy, dU, is equal to the voltage at any time V, multiplied by the small amount of charge dQ. The power is how much energy is moved per second. This is just du by dt, which we can see is equal to V times dQ by dt. Of course, the flow of charge with time is the electric current, so the power is simply V times I. In an AC circuit, nothing changes except V and I are continuously varying with time, so, as you'd expect, the power also varies with time. We call this power the instantaneous power in AC circuits because it tells us the power at each moment. Before dealing with this example, let's go to a simpler one with only a resistor. In this case, the current and the voltage are in phase. If we plot the product of these two curves, we get this for the power. It makes sense that the power is always above zero, as the resistor is constantly dissipating heat. Specifically, this power graph is V0 I0 sine squared omega t. But this isn't particularly useful on its own. What we really want to know is the average power dissipated by our circuit. Looking at our power curve, you can probably guess that the average is around here. We'll see how to calculate this in a moment. For now, let's just appreciate that the average is going to be a positive value above zero. But let's see what happens when we replace our resistor with a capacitor. As we saw in the last part, I is C dV by dt, so the current expression changes like so, where there is now a phase shift of 90 degrees. If we now plot the power, we actually get a sinusoidal curve with twice the frequency. Here, we see that the power dips below zero for half of the time. So in fact, we can immediately observe that the average power is zero. Why is this happening? Well, for any moments the capacitor has an electric field, there must be energy stored in the capacitor, because an electric field stores energy. But the electric field can also diminish during the AC cycle. If the electric field is ever diminishing, it means energy is flowing out of the capacitor. In this circuit, as there is nowhere else the energy can go, it must be flowing back into the source. This is what is happening when we have this negative power. Our source is actually gaining energy at these points in the cycle. So in fact, overall, no energy is gained or lost. The average power is exactly zero. By the way, this is the equation we get for the power curve, which we'll derive later. For an inductor, we get a very similar scenario. In this case, the current lags the voltage by 90 degrees, because the magnetic field in the inductor takes time to grow and collapse. Just like the electric field in the capacitor, this magnetic field stores energy. As you could guess, we once again see a sinusoidal power, where the average is zero. As the current grows, the magnetic field is being formed, so the power is positive, and when the field diminishes, the power is negative, as energy is leaving the field. For an inductor, the equation for power can be written like so. Before delving deeper into this, let's see exactly how we can find the average power. We'll use the resistor circuit as it has a non-zero average. Mathematically, to take the average of any waveform, we can integrate over one wave period, which has a time period capital T, equal to 2 pi over omega, and then divide the integral through by that time period. Substituting in our power formula, we get the following. If we take the constants out front, we get the integral of sine squared omega t from 0 to capital T. The answer to this, which you can prove yourself, is exactly 1/2. So this is our resulting power expression. If you watched part 3 of this series, you'll know that we already did this derivation, and realize that it matches our DC power expression besides this factor of 2. To recreate our DC expressions, we just substitute in the root mean square voltage and current, instead of our maximums, V0 and R0. The root mean squares are literally the maximum divided by square root 2, so in our power expression, we now recreate the DC expression. I know this seems a bit random, but we'll see later that this makes the maths much easier. Either way, this is our average power. But what happens in a more complex system, like this RLC circuit? How do we find the average power for any system from the current and voltage? Well, no matter what goes on in the circuit, we know that the voltage source is the same. As for the current, we'll just draw in an arbitrary one for now. We know it must be a sinusoid with frequency omega, but we don't know the amplitude or the phase shift. These are the only two things that vary depending on the circuit. We discussed this in the previous part. If we try and calculate instantaneous power now, we get this rather ugly expression, which is not convenient for calculating the average. But using some trig identities, like so, in a clever way, we can get a much neater expression. In this identity, if we let A equal omega t and B equal omega t plus phi, we can rewrite our power like so, where we have V0 I0 over 2 times cos phi minus cos 2 omega t plus phi. I'm aware this now looks even more complicated, but it turns out that the average is in fact very simple. If we average over time, we only have to look to this cosine 2 omega t part, as it is the only bit that changes with time. Best of all, the average of any cosine function is 0. So this part of our equation completely cancels out, and we are left with I0 V0 over 2 times cos phi. Once again, we'll get rid of this factor of 2 by rewriting it in terms of the RMS values. So in fact, the only difference between our resistor circuits and the general equation is this cosine of phi. So where does this come from exactly? Well, let's look again to our plot of the current and see what happens as we gradually vary the phase shift. At zero phase shift, we get a completely positive power curve, where our average is above 0. Using our formula, we see this is equal to IRMS times VRMS. Now, let's vary the phase shift gradually towards 90. When we do this, we see that the power becomes sinusoidal, and the average drops to 0. The key point is, everything depends on the phase shift. We define cos phi as the power factor, as it determines exactly how much of the input power is actually being used. If phi is 90 or minus 90, the average power drops to 0. Meanwhile, if the phase shift goes to 0, cos phi is maximized, so the average power becomes its maximum. The maximum power case directly corresponds to a purely resistive circuit, while the 0 power corresponds to a capacitor or inductor circuit. But this raises an interesting question. Here the power is 0 for capacitors and inductors, but we still know the electric and magnetic fields are growing and collapsing. So how do we take into account that effect? After all, power is still flowing from the source to the fields, even if it flows back. For this, we need some more specific definitions of power. Firstly, the average power we've calculated, we'll call the real power P. It is the power dissipated by the circuit. I've color-coded this purple for reasons we'll see in a moment, but to be clear, this is the same as the average power. However, to consider the power going in and out of fields, we'll define a separate quantity, the reactive power, Q. And finally, to pull it all together, we'll define the apparent power, S, which is the total power put into the system by the source. We already know the real power is IV cos phi, but what are the others? Well, as we know, all the power is real if phi is 0. So the maximum power, which must be equal to the apparent power, is simply VRMS times IRMS. For the reactive power, we know it is equal to the apparent power when phi is 90 or minus 90. Logically, the only expression that would match this result would be IRMS VRMS times sine of phi. So all in all, we have 3 types of power in AC circuits. You might already be able to see how these quantities link together. In the previous part, we defined impedance as the total circuit opposition to current flowing. This considered 2 parts, a resistance and a reactance. These relate to one another like so, making up a neat triangle on the real and imaginary axes. The magnitude of impedance, Z squared, is simply R squared plus X squared, and in complex number form, Z can be written as R plus J times X. The angle between impedance and resistance is phi, the phase shift. If you're unsure of any of this, do check out my previous video. It turns out that our 3 power expressions work in the exact same way. If we calculated P squared, Q squared, and S squared, you'll see that the equations match up like so, such that S squared is equal to P squared plus Q squared. So just like impedance, the powers make up a right-angled triangle. Best of all, these 2 triangles have the same angle, phi, the phase difference between the voltage and current. Just like the impedance, we can write the apparent power as a complex number as well. This complex number, of course, has a real part equal to the real power, and an imaginary part equal to the reactive power. There's one more brilliant trick we can do here. As we saw last time, the impedance allows us to make an AC version of Ohm's law, which is V equals I times Z. We'll use RMS current and voltage, so we can substitute this into our power equations. Firstly, we can write the apparent power, which is just I times V, as I RMS squared Z. For the real power, IV cos phi, we can replace V with I times Z, and then replace cos phi with R over Z, because cos phi is just the adjacent over the hypotenuse in our power triangle. We can then simplify this to I squared R. Finally, we can do something similar with the reactive power, where we replace sine phi with X over Z, which yields I squared X. Do pause the video and convince yourself of this if you're not sure. So in fact, we can use our basic DC expressions for the power, and we can convert between our impedance triangle and our power triangle by simply multiplying by IRMS squared. It really is quite beautiful how neatly everything fits together. So let's now summarize everything we've learned. In any circuit, the instantaneous power is simply the voltage multiplied by the current. In AC circuits, both of these are constantly changing, so the power is also constantly changing. A more useful quantity, therefore, is the average power, which tells us how much energy is actually being consumed. For any steady-state AC circuit, this turns out to be Vrms Irms cos phi. We call this the real power because it represents the energy that is permanently dissipated by the circuit. To represent the power that is not lost, i.e., that which flows in and out of capacitors and inductors, we use reactive power, equal to Vrms Irms sin phi. Together, these combine to give the apparent power, the total electrical activity in the circuits, Vrms Irms. These three quantities form the power triangle, where S squared equals P squared plus Q squared. This triangle has the exact same angle as the impedance triangle, which is the phase difference between current and voltage. Finally, using the AC form of Ohm's law, we can rewrite the powers in an even neater form. I squared R for the real power, I squared X for the reactive power, and I squared Z for the apparent power. And with that, we now have a complete physical picture of how energy moves through AC circuits. But there's one more remarkable phenomenon still waiting for us in RLC circuits. What happens when the inductive and capacitive reactances exactly cancel at just the right frequency? In this scenario, the circuit enters a state called resonance, one of the most powerful and beautiful effects in physics. That's what we'll explore in the next video. By the way, I will soon be releasing practice problems for this video on the free Decipher Physics iOS app, which already contains practice problems on capacitors and GTC physics. Thanks for watching.